Good evening. I'm Alan Howells, Pro-Vice-Chancellor at the University, and I'm delighted to invite you all here today. I'm only going to say a few words of introduction. I'm going to hand over to my distinguished colleague here, Leslie Griffiths, Assembly Member for Wrexham, who's going to introduce the lecture this evening. But if I can say, it's a pleasure for us to host these events. These are really an important feature of our university calendar, and I'm delighted that so many have been able to make it this evening. So without further ado, I'd like to hand over to Leslie. Thank you.
Thank you, Alan. As Alan said, I'm Leslie Griffiths and I'm the Assembly Member for Wrexham, and I'm also the Deputy Minister for Science, Innovation and Skills at the Welsh Assembly Government. And I'm delighted to have been asked to come along and introduce the speaker this evening. The reputation of a university depends primarily on the quality of its academic staff. And here at Glyndŵr University, we are proud to have some exceptional academic staff. And I know the university has been working very hard to recruit top specialists in their field. And this evening, we have one such individual giving his first public lecture at the university, Professor Richard Day. And with my ministerial hat on, yesterday I was in Port Talbot and I attended an unveiling of a plaque at a company that dealt with composites. And as soon as I said I represented Wrexham, Richard Day's name was mentioned in very distinguished circles, so that was very good, Richard. You originally graduated as a physicist from the University of London, and after a move to Bristol University to study the physics of materials, Richard returned to London to undertake a PhD in the stability of molecular electronic materials. He then joined the University of Manchester, where he stayed for 23 years. That doesn't sound right. Is that right?
That's right.
You don't look old enough. His interests there spanned polymer engineering and composites. During this time, Richard was one of the founders of the Northwest Composite Centre, established by the Universities of Manchester, Liverpool, Lancaster and Bolton. And the centre is one of a network of regional composite centres across the UK, which now includes Glyndŵr University. Since joining Glyndŵr in 2009, Richard has become an indispensable member of the academic staff. His roles include academic leader for mechanical and aeronautical engineering and associate director of the graduate school. He's now based at the new Advanced Composite Training and Development Centre in Harden, which is the result of a groundbreaking partnership between the university, Airbus, Deeside College and the Welsh Assembly Government. Research led by Glyndŵr University here will be targeted at developing faster manufacturing and processing techniques for composite materials, which will help to meet future demand for aircraft. So I'm delighted to welcome Professor Richard Day to the floor. Thank you.
Thanks very much for your introduction, Leslie. When I was asked to give this lecture, I prepared it, and then I thought, well, how am I going to explain what it's about and what the philosophy is? And as Leslie said, I started off life as a physicist, and this book was something that came out about the time I was studying, and a lot of us read. I think just about everybody on the course read it. Zen in the Art of Motorcycle Maintenance. Well, how does that relate? Well, actually the title has almost nothing to do with what's in the book. As the author says in his introduction, it shouldn't be associated with the great body of factual knowledge about Zen Buddhist practice, and it's not very good on motorbikes either. And that's a bit like this talk, in that this is a personal journey through things that I think are interesting in the aerospace industry. So it's not very historically accurate. And also I'm aware that there's a wide variety of people in the audience. I see some people here are stress engineers in composites, and others are from a completely different background. So I've tried to keep it as general as possible and not put into too much detail. So hopefully it's factual, but it won't go into too much detail. One thing which comes through in the book, however, is the pursuit of quality and what quality means. And you'll find that quality and how to make things well is intrinsic to what I do. The other thing that comes across, which is probably not so good, is it's clear that the central character has sometimes been completely mad. So hopefully that doesn't come across. They've clearly had some kind of a breakdown. Having said that, as Leslie said, I've got quite a broad background, and so I started off as a physicist. I worked on molecular electronic materials and then moved into composites. And that means that in my world, when you shine light into something, it comes out a completely different colour. Plastics conduct electricity, and materials have different stiffnesses depending on which way you load them. So maybe the madness is coming through already. Okay, so let's move on. So that's my introduction. So I want to say a few words to start off with about what a composite is. Then I'll go through a fairly personal view of the development of aircraft and materials in aircraft. A few words about today's issues, and then I'll move on to just skirt around briefly what we're doing at Harden, and then a few words of conclusion. Okay. So let me start off by defining what a composite is. My definition, which is a fairly commonly adopted one, is it's a combination of materials designed to result in a material with better overall properties than the starting materials. So we're putting things together, and in some way we're trying to make a product which is better than the things we started from. The things we tend to put together are some kind of reinforcement, and then something to protect the reinforcement. So it might be, so I'm going to come around here. Okay. It might be long fibres, it might be whiskers, it might be particulates. So this is what fibres will typically look like. The one on the left is some glass fibre, and the one on the right is carbon fibre. And there's a whole range of ways of then turning these into a composite. And if anybody's interested, we've got a very good MSc course which you can come and find out about it. On the whole, we tend to weave the fibres together in various textile structures and infiltrate them with resin and cure them. And this is the material which is often used in making aircraft. It's prepreg, and we have to store it in a freezer because otherwise it will cure and it will go off. So that's my hopefully 2-minute introduction to composites, and just to set the scene for those of you that don't know what they are. But as I say, there's an entire course if you're interested. Development of aircraft. Well, I guess that really started with the Wright brothers' experiments, and this is an early glider that they put together to try and understand the dynamics of flight. And then they moved from that to this machine which flew a reasonable distance. And note the date, because you're going to need that later, 17th of December 1903. So remember that, because towards the end of the talk you'll need it. But clearly before they made planes, they did something else. And the Wright brothers were bicycle makers. They had a bicycle shop. Okay. But what do we get from the Wright brothers? Well, they put together airplanes, an airplane from wood and from cloth. So a wooden frame and then cloth over it in order to provide the flying surfaces. They changed the shape of the wing in order to control. So nowadays we use flaps. But actually there's a lot of discussion and a lot of research work on wing warping again, under a different name, but that's what it is. They also were the first people to understand control. I think my laser pointer is a bit too faint. They made their own engine in their bike shop, and they made it with a wooden frame, a spruce frame. But actually, if you look into the structure of wood, wood itself is a composite. It's essentially cellulose fibres in a lignin matrix. And when you make paper, all you're doing is you're extracting those fibres out and putting them together. And then they use muslin for the control surfaces. So this is the three directions that you can change in flight: roll, pitch and yaw. And that was really understood first by the Wright brothers from their experiments with a kite. But going back to the wood fibres. Well, wood fibres are just paper when you put them together. Here again there's something fortuitous, in that before I came here I lived for about 4 years in a paper science building with a paper machine, which is the hottest, dampest thing you can imagine, and amongst paper scientists. And one of the really critical theories of composites is known as the Cox theory. It was proposed by H.L. Cox in 1952. But the Cox theory is all about paper, not composites. And it turns out it works really, really well for composites. It's dreadful for paper. It doesn't work at all. And it's because the assumptions are wrong. Because what Cox assumed was that the fibres were in some kind of a matrix. But you can see from this picture, it's just a network of fibres that touch at different points. So composites and wood and paper are actually quite closely related. So I want to move on a bit further and show you this picture. This is a Bristol box kite. That picture was taken in the museum in Bristol, and most of you probably don't know that I was born and bred in Bristol. So I spent a lot of time in this museum as a child. There are no longer any original Bristol box kites left, but there were 3 box kites remade for the film Those Magnificent Men in Their Flying Machines. And after the production, one of them ended up in the museum at Bristol, one's in the Shuttleworth collection, and another one went to Australia. So why am I showing you this? Well, this goes back to Sir George Wright. Sir George Wright originally ran an electric tram service. He had the first tram service in Bristol, and then he expanded out to London. And he also went into the manufacture of buses. As a child in Bristol, as a teenager, I went to a school in the middle of Bristol. And its playing fields were actually outside of Bristol, so we had to go by coach out to the playing fields. And we used to pass the Bristol bus factory, which, okay, this was the 1970s, but it still existed then. It doesn't now. And it was really odd because they had to move the buses around from place to place on site as they were being made. So you'd often pass the site and there'd be a double-deck bus, but it would just be the floor and the wheels with somebody sitting on a deck chair driving it round from one point to another as it was being made. Anyway, so Sir George Wright started building aeroplanes in a tram shed. The tram shed was in Filton in Bristol. Okay, Filton may register with some of you. Well, the British and Colonial Airplane Company went through lots of changes. It became the British Airplane Company, eventually became British Aerospace, who were then one of the founders of Airbus. So actually, this was the first Airbus product. Now you may think that the madness is coming in again, but some of my time, as Leslie said, is spent out at Harden, where of course we get plentiful supplies of the Airbus House magazine. So which of course I dutifully read when I'm having a coffee. And what did I find in November's issue but this? The landing gear systems test facility at Filton is named after Sir George Wright. So it's not just me that spotted that. So let's move on a little bit now. And so we had lots of wooden biplanes, and then suddenly on the scene came the Boeing 247, which was a revolution. Aluminium became readily available, and suddenly we went to a system which looks quite different. So it's metal, it's got a reliable engine, it's got trim tabs, had an autopilot, even then, de-icing, retractable landing gear, not landing gear that looks like it's been stolen off a pram, and it was generally quite comfortable. And it was actually faster than the fighter that was in service at the time. So we gradually went over to aluminium aircraft, but well, I didn't mean to say that the biplane died out completely, because Antonov started making this biplane in 1947 and had a huge production run. In fact, I think only the Hercules has had a longer production run than this. I'm told this is the biggest thing you can fly on a private pilot's license. Well, I know there are a couple of private pilots in the audience. So, made out of aluminium, but a few years ago, production stopped in Russia and moved to China, where it's now being produced as the Y5. So they're still, as far as we know, in production. Except that they've actually gone back, for some versions, to wood and cloth. There's a fleet of these run by the North Koreans. And they've gone back to wood and cloth because it's stealthy. There's no radar cross-section. So, very simple solution. So it's like when the space race was on, then the Americans devised a very clever ballpoint pen to write in space. And the Russians took a pencil with them. And likewise, one of the areas I used to work on is composites, and particularly protection of composites at very high temperatures, a couple of thousand degrees C, ceramic composites, which is for applications like the space shuttle. The American solution is to put fancy alumina tiles on. The Russian solution, I was very lucky at a conference to meet, as the Berlin Wall was coming down, and also Russia was becoming a bit more open. A lot of very famous people from Russia were at a conference I was at Stuttgart. And so I asked them, well, how do you cope with it? And they said, oh, we put carbon-carbon composite on our reusable re-entry vehicles. And we know that it burns through 1 millimetre of this in 1 minute. So we put 6 millimetres on, because it takes about 3 or 4 minutes for re-entry. If it's taken 6 minutes, you're dead anyway. Okay, so moving on, just take you through some airplanes that you'll recognise. So here's the Boeing 707, which is probably one of the first of the airplanes you'd recognise as a modern airliner. First flew in 1957, had an aluminium skin, and there were about 2% of glass fibre composites in here. So mainly around the nose. But let's just look at that again, because I gave you the name of this alloy, 2024T3, and I need to explain what it is. And aluminium alloys have this naming convention, XXXXYY. And the XXXX isn't a swear word, it tells you what the material type is. And the YY tells you about how it's been manufactured. And there are various series, so 1000 is more or less pure aluminium going through. But some of these can be precipitation hardened, the 2, 6 and 7,000 series. And what we're doing is putting one metal in another in order to improve the properties. Because in metals, if you have a pure metal, it's not very stiff or strong. What you need is defects. So we can put lots of defects in, and the defects are there naturally, and we can increase the number quite easily. If you stop the defects moving around by putting something else in there, then you can make it stronger than it was before. Okay, well, a metallurgist would tell you this is an alloy, but I'm telling you it's a composite. Okay. Because that falls within my very liberal definition of a composite that I had before. Okay, so aluminium alloys, no, it's composite. So I'm just going to move through. 737 came in 67, and the 320 came in, and there are a lot more composites used then, so some of the control surface and the back end is a composite. And 777, which didn't have so much in. And what I've done is I've plotted the composite weight in various planes, and again it's been very selective against the year when they first flew or are due to fly. So you see 707, there's a little bit. Surprisingly, Concorde had about 8 or 10% composite in. The 300 series, between 10 and 20%. 777 was down at 10. But then 380 has a reasonable amount of composite in. And the 787 and the 350, which is why we're at Harden with our training centre, are both around about 51, 52%. So we're getting quite good at putting composites in things, so we think. So let's look at something else. And somebody I know at Eurocopter was kind enough to send me this slide. And actually, although we think we're doing quite well in commercial aviation, actually for 20 years there's been 50% composites in civil helicopters, and even more in military helicopters. And they still complain that they're difficult to work with, and it wouldn't be easier if we made this out of metal. But that's the way things have gone. And of course, in a helicopter, it's all down to pure thrust. There's not much in the way of aerodynamics, so you have to reduce the weight very quickly. Okay, so what about today's issues? What's important? Well, designing with composites is critical in order to get sensible manufacturable solutions. At the moment, we're going through an interim phase where a lot of the structures we make are hybrids between metals and composites. And these are often known in the industry as black metal designs. And what we really need to do is to move forward and use composites more fully, certainly in larger aircrafts. And that's quite a tough challenge, to make a big aircraft in just carbon fibre is tough, and there are lots and lots of issues. But we also need to be able to manufacture these rapidly. So just showing you where we've come so far. This is Honda's jet, 2003. This is a small business jet where all the fuselage and wings are all composite. So apart from the engine, this thing's nearly all composite. This first flew on the 3rd of December 2003. 2 weeks short of the centenary of flight. So we've gone from something which was fairly uncontrollable and flew just off the ground for a few meters to something like carbon fibre jet in 100 years. So that's a hell of an achievement. So why are we going down the road of putting composites in aircraft? What is it that's driving us? Well, there's two answers to this. One revolves around this, which is a vision for 2020. It's a document produced in Europe. This is an interesting document, but throughout it, there's these little panels dotted around the document with various goals and targets and so on. And one of them, the one at the bottom here, It's a 50% cut in CO2 emissions per passenger kilometre by 2020. That's a hell of a target. It's a half the emissions. Oh, and by the way, you've got to cut nitrous oxide emissions by 80% as well while you're doing it. So how can we do that? Well, there's only one equation in here, so bear with me. The range of an aircraft depends on lots of things. One is the aerodynamics, how good the lift is compared to the drag. The thing in red tells you about the engines and how good they are, fuel consumption, temperature of the fuels and things like that. And then the weight of the aircraft. If you could half the weight of the aircraft, you double the range. It's not easy. But if we want to reduce our CO2 emission by 50%, we've got to reduce the fuel burn by 50%. The general view in the industry is that probably we'll get 20% improvement by 2020 in engines. And don't forget, this is an ongoing process. It's not going to suddenly happen. The engines have been improving for years, and likewise with airframes, as different models come out, each one is a little bit better, a little bit lighter. So there are a whole range of 320s and Boeing 777s and so on. But what we need is to adopt composites to give us lower weight, but it also helps with the aerodynamics. Well, how does that help? One of the things that you can do is to make more complicated structures more easily in composites. I was very fortunate a year or two ago to be taken off on practice by the Honda F1 team, and I took a picture of this in the pit lane. I was told anything in the garage, no, you can't do. Anything on the pit lane was in public view. So somebody left the nose cone outside, so I quickly took a picture of it. And you can see that the nose cone, the areas go down and round, and there's curvature in lots of different directions. And that's something that's quite easy to do with composites. If you want to do it in metals, it's much more difficult. There's a lot of machining to be done. There's a lot of waste, and I'll come back to that in a minute. So let's think about reducing CO2 and how we can do it. General estimate is that probably aviation contributes about 2% of the global CO2 emissions. How does that compare? Well, it's a lot, but shipping probably contributes something like 4%. So you hear a lot of people talk about aviation and the carbon footprint, but actually the carbon footprint of shipping is twice as bad. So what can we do? Well, actually air traffic management is important, the right choice of flight path. Eliminate unnecessary weight. So nowadays, rather than taking on boxes full of manuals, you take on an electronic flight bag, which is either an organizer or a laptop, which has got all the manuals and things on the hard drive. And there's some other things that you perhaps wouldn't think of in order to reduce the weight of a plane. One is to wash the engine out, which sounds mad. But you get a build-up of soot in the engine, and if you wash it out, you reduce the weight of the aircraft. Something like, well, for American Airlines reckon that this saves them about 4 million gallons a year of fuel, just washing the engines. Jet A, about an hour before the lecture, was £4.30 a gallon. At LAX, it's $6.94 today, and that translates about £4.30 a gallon, which means you're saving over £17 million by washing your engines. Likewise, if you wash the aeroplane, they don't look dirty, but they're big structures, so you don't need much dirt to add quite a lot of weight, and you might be carrying 300 kilos of dirt. The other thing is, don't carry things that you don't need to. So, for instance, American Airlines again noticed that they didn't actually use all the water that the plane could carry for service. So they fitted something on the hose. So it's filling up water on a plane, it's like filling up petrol in your car. You put a hose in and fill it up. And they put in a little device which costs them £1, and it turns off the water when the tank's 3/4 full, because they don't need the full tank. And they reckon that saves them about £1.4 million in fuel a year. And obviously, also you're carrying less weight, so the CO2 emissions. And also, think about the fuel load. So there's ways you can do it. Also, maintenance affects fuel burn. For instance, if you have to leave the power unit on, because there's a fault somewhere else, that's costing you £4.30 a minute to run, and it's producing CO2. And just to give you an idea of the size of the problem, 1 tonne of weight gives you about 420 tonnes of CO2 per year. And that means that if you take an extra carton of milk on every flight, it results in 0.8 of a tonne of CO2 every year. Okay, so looking at what's important in materials, when you do some analysis, the thing that's critical for a wing, say, in bending, is the cube root of the stiffness divided by the modulus. And again, if you come on the MSc, you get to prove that. So let's look at some values. There's stainless steel, titanium, aluminium. Stainless steel has been used in early planes. Titanium is used particularly around the landing gear and so on. But aluminium in most of the planes that are flying at the moment. But you see that carbon fibre composites, 3.6 against 1.5. So that's a hell of a difference. So it means that you can make your plane much lighter for having the same stiffness and strength and structure. And then the one at the bottom shows you that actually the wood's better than all of them. So maybe we got it right in the first place. And you can see certainly quite large structures can fly in wood. This was the Spruce goose, made by Howard Hughes for the American government. They did various trials on the 2nd of November 1947, resulting in it flying for a couple of miles, about 50 or 100 foot off the air, and it never flew again. So, very strange. As is the name, Spruce goose. It leads you to think that maybe it was made from spruce. Actually, most of the structure was made from birch. It's one of these things that caught on in the press, the Spruce goose, the alliteration, and it stuck, but actually it's a largely birch structure. Okay, so I've told you the political and social reasons why we ought to think about moving to lighter planes and to composites. And then there's a commercial reality. This is the crude oil price since 1947 up to last year. And since then, basically, it's shot back up to about $100 a barrel. And there were peaks. This only captures it by quarter, but there were peaks when it was higher. At one point, that spike actually went up to $147 a barrel. But you can see that over a fair period when we've been flying, oil has been about $20 a barrel, corrected to, in this case, it was 2008 prices. So when most of the planes we're flying today were designed, it was comparatively cheap. But now that we've got back to this high price, back to the $100 a barrel, that's a hell of a price to be paying for your fuel. For your fuel to go up 5 times in price over the life of the aircraft. You've gone from running a nice business to the saying they say about how do you become a millionaire? You're a billionaire and then you buy an airline. And it's an easy way to lose money, and a lot of airlines don't run in profit. Something else just before we go off of this is something that's known as the buy to fly ratio, which is the weight of metal that you buy compared to the weight in the final component. And there's some extreme values. Fan blades are pretty good. So you buy 1.5 times as much as you want. But for some structural parts, you've probably only got 5% of the original billet left. So you buy a big block of material and you mill it away to make your component, and you make lots and lots of swarf. You couldn't make that up, could you? In terms of a manufacturing process, 95% waste. Okay, it can be recycled. Whereas composites, you can mould to shape with much lower waste. So, my boss, who unfortunately can't be here tonight, is very sceptical about these plastic aircraft, and every time I talk to him, he just looks more and more nervous, and he goes kind of more and more white. And I think he's probably read this story, which is something that hit the papers about 3-4 years ago now, and it was a former engineer in the Phantom Works was saying that he thought that perhaps composite plastic materials were not a good idea in planes. Okay, so let's think about this and about other industries where they've been used extensively already. And think about motorsport. Okay, this is a statue of Fangio, who was a very famous driver, drove in the 50s and beyond. Mainly for Mercedes. The picture is actually just taken just behind the garages at the Circuit de Catalonia in Barcelona, which is where I went to watch Honda practice. And it's an area that you don't normally get into unless you go into the garages or into the area where the camper vans are. But driving in those days was a really dangerous business. Most people were killed. As it turns out, Fangio was either very good or very lucky, because he actually lived until he was 84 and retired in Argentina and actually died of old age at home. But a hell of a lot of the people that he raced with didn't. And perhaps something that brings that home is the next slide, which is, I've just made a list of the Formula One drivers' deaths in the past 30 years. Some of those names you'll recognise. Well, you've probably worked out from what I said about school buses and so on that I was a teenager in the 70s, watching Formula One. And every race had a very similar pattern. We talk about it being boring these days sometimes, and how do we get it more exciting? But no, they also had a similar pattern, which is at some point there'd be a huge crash. They'd have to stretcher somebody off, and there was always a hospital at every circuit, and there'd be a surgeon standing by. And during the course of the race then, you'd get commentary on the race, and you'd also be told how the driver was doing and whether they'd had to be airlifted off to a bigger hospital and things like that. And it was practically every time they raced. And you can see there were a huge number of driver deaths. And I'll just pick out one in particular. This is Tom Price. I picked him out because Tom Price came from Ruthin, which is just down the road. And he died in a really strange accident. He was killed by a fire extinguisher. How? He was racing, and one of the marshals was running across the road. He hit him, killed him, and the marshal was carrying a fire extinguisher. The fire extinguisher then hit him and killed him too. Since then, lots of things have happened in Formula One. One is the rules are very, very tight. But also, there was a step change in technology with the introduction of composites in 1981. It took a few years to get it right, but now you have horrendous crashes and people walk away. So this was actually at the same circuit, and you can see that this car has hit the barrier, came off, it hit the barrier at about 200 miles an hour, this accident. But the central zone where the driver was is pretty much intact. Everything else around it has been crushed and absorbed the energy. And actually, this was a report in the next day's press, I have a slight headache and a stiff neck, but other than that, I'm doing well. Well, in the 70s, he'd have been dead. So that's the difference that Composites has made to Formula One. There are other differences as well, and the rules are very tight. And if you go onto the FIA website, you can download the rules. They're not protected, they're in a Word document. And that Word document is done in track changes, so you can see what last year's rules were. And you find that if you look at it, the energy and the impact deceleration that these cars have to take every year, they just ramp up slowly. So a mixture of engineering, getting the right material, and making sure you do lots of testing before you start. And we've gone from a sport that was really dangerous to one that you can survive the most amazing crashes in. So maybe there's something for us to learn there in aerospace. I'm not advocating crashing lots of airplanes, by the way. And also, I would say it's a very heavily regulated industry, and safety is absolutely key. As I can tell you, working up at Harden, the behaviours that are instilled in the employees are very critical. And just to show you this, I've stolen this from a presentation by somebody in the audience, so thank you. The red curve shows you what happens when you crush a composite cylinder. And you can see you get an initial increase in load, and then it crushes very smoothly. Whereas the grey one is what happens when you take a metal cylinder, and it goes and jerks. So some acceleration, deceleration, some acceleration, deceleration as you go. So the crushing properties of composites are actually much better than that of a metal for this kind of application. Okay, so let me move on a bit and talk about manufacturing processes for aerospace composites. Typically, we use autoclaves, the best quality components, but they're very slow. Heat transfer in an autoclave is a very, very slow business. The challenge is to make this much, much quicker. So at the moment, Boeing are producing the 787, Airbus are working hard on the 350. But the demand for these is comparatively low. These are long-range planes, big planes, intercontinental. So they're built at a rate of about 1 or 2 a month. The 380, I think there were something like 13 deliveries in the first year, and I think that ramped up to 22 in the second year. So they're making about 1 a month, 2 a month, and these things are likely to be the same. But for short-range aircraft, things like the 320, you build at rate 20. Well, rate 20 is an industry abbreviation. What that means in reality is you're making 40 a month, or more than 1 a day. And suddenly the challenges become huge, and your manufacturing techniques need to be revolutionised in order to cope with that. So how are we going to speed up making composites in order to make composite components at the speed we need to? Well, we're going to have to improve heat transfer. And if you think about an autoclave and what you're doing, it's basically like the oven at home. So you'll have probably gathered that food is quite important to me. And cooking. So at home, well, you use an oven, but actually it's not very good. Because you can put the hand in the oven, again I'm not advocating this, but you put the hand in the oven, and because heat transfer from a gas to a solid is pretty poor, you don't burn your hand, provided you don't touch the chicken or the sides. No, that's bad, don't do that. So what do we do at home when we want to speed up cooking? Well, 2 things. Either we deep fat fry things, or we microwave them. You may think I'm going off at a tangent here, but actually that's exactly what we do with composites. So deep fat frying of composites, well actually that's a technique called Quickstep, and I'll be delighted to talk about that technique. And also there are basically 2 research groups that are working on this There's a group in Manchester which I used to work on, and there's also a group in Australia, and both groups are represented tonight. So if you want to chat to us afterwards, then please do. So that's okay. So you can then make things much more quickly, because like deep fat frying, you get better heat transfer, and things cook quicker. And then
What sort of temperatures are you achieving? Do you need to achieve?
180. You can get 180. 190 at a push. So aerospace composites are fine. And the other thing to do is maybe microwave them. Well, microwaving composites isn't quite so easy. It's something that I've been doing for about 15 years now, maybe slightly longer. I thought, how can I show you the problem with microwaving composites? And I guess you're sort of familiar with it, because most people have put a plate with a bit of metal or something in the microwave and it sparks everywhere. And I thought, well, how do I show this? And actually the next couple of slides came about by accident, because, to be honest, about a fortnight ago I lost my car keys. I couldn't find them anywhere. Now, you might have some trouble believing this, because this is my bunch of keys, and somehow I managed to lose those at home. So I live about 50 miles away, 55 miles away from here at the moment, so I had to come in by car. So I borrowed my wife's car, which is very nice, much bigger than mine and much more comfortable. The only trouble is I normally listen to some music on the way in, and I couldn't, because my music was locked in the car. Well, anyway, to cut a long story short, I spent 2 journeys too many with Robbie. So I thought I could maybe use this to some advantage. So this is what happens when you put something that's conducting in the microwave. I'm glad to say my wife hasn't led this talk tonight. This image is just about 5 seconds long, and it's just repeating. So you have a few seconds where nothing happens, because it takes a while for the microwaves to turn on. And then after about 3 or 4 seconds, essentially you've done this to the CD. Please don't tell. And the same thing can happen in carbon fibre composites if you put them in a microwave. This technique is actually used, certainly in America. Microwave pizzas are quite popular, and they basically use the same technique. They put some cardboard, which has got a conducting layer on the bottom inside, and that basically helps to crisp the crust. So that's basically how it works. Only those things, the metallized cardboard will stand about 30 seconds before it breaks down and it stops heating. So what we've done is we've looked at microwaves, and very briefly, the picture on the left tells you what the microwave field in an ordinary microwave looks like. Ordinary microwaves, a domestic microwave, works at 2.45 gigahertz. And I don't want to explain too much, but basically you can see that there's big patches of red and blue and so on. And that's what causes the arcing, because you get currents flowing from the area where there's a lot of power to a small amount and back again. If you go up in frequency, and so we pick devices which work at higher frequency, then you start to even that out. If you start changing the frequency from time to time, you can make it really even. And now you can put a lump of metal or a carbon fibre composite in this, and it doesn't arc. There are a few other tricks as well, but that's the main one. And that's the proof. That's some carbon epoxy which was made in a microwave chamber that we built. Okay, so on to where we're going. Leslie and I both mentioned the Advanced Composites Training and Development Centre, which is a joint activity between ourselves, Airbus, Assembly Government. And there's 2 things going on in there from our point of view, and that's research into composites, manufacture, assembly, evaluation, and also there's teaching space to run an MSc in composites. So that's just sign outside, and you can see where it is from this picture. The lurid gates are the crash gates for the runway at Harden. So we're just outside of the boundary there, and if the picture was a little to the left, you'd see the control tower. So that's where we're situated. Opened on the 7th of October 2010. You may recognise some of the blokes in those pictures. For those of you who don't, on the left it's Carwyn, who's the First Minister, the Vice-Chancellor, top right, and then a few of us with Mark Barclay, who's Vice President of Airbus, in the bottom right. So this is what it looks like: lab facilities, IT, lecture rooms and so on. And this is Airbus' bit, which is a fantastic training facility for preparing people for the 380 wing build, which is starting soon. So just want to say a few words about other associations. Obviously that one's important to us, but some of you will know that I came from the Northwest Composite Centre in Manchester, and Leslie mentioned it, and we still see that as an important link, and there are 2 or 3 people in the back who have come over from Manchester. But also we have a relationship with Bolton, Liverpool, Lancaster. We work closely with the Welsh Composites Centre in South Wales, and we talk a lot to them. Interestingly, about 2 months after the opening, I went to a presentation given by the director of the National Composite Centre, and he put this slide up, which he's kindly sent me, which shows that we already appear on the map of regional composite centres. So moving on a bit more to what we do, let's think about what the university does. The vision statement for the university is that we're to become an indispensable, as a significant, relevant and expert partner in regional and national economic and social development. And that's the crest. For those of you who don't read Welsh, the Welsh underneath says confidence through education. So, themes. General area, we're interested in rapid manufacture, assembly and recycling of composite structures. And the assessment of the fitness for purpose of these structures, because it's no good making something fast if you make rubbish. So it's back to this quality thing that I said at the beginning, that you need to make it fast, but you need to make it well. It's got to serve the purpose. And of course, with the university's emphasis on industry and working together, then clearly close coordination with industry and its requirements. You should not ever make the mistake of thinking that's entirely the aerospace industry, because although we're based with Airbus at Harden, we're interested in a whole range of things and sectors. And I've just put up some pictures on the right-hand side to show you some of the work that I have done in the past. Overhead lines tend to have ceramic insulators supporting the cable. But National Grid, about 15 years ago, started experimenting with composite insulators. And I got involved in the testing of some of these. And I have to say, it's some of the best fun I've ever had. The picture at the bottom looks like it's not very well taken because it's all sort of fuzzy and there's blobs. Now that's a pretty good picture. What was happening was that there were 4 fire hoses trained on that, and the blotches you can see are specks of water. So we had fire hoses on it, and then we put 200 kV across it. And just waited to see when it broke down, and we gradually cranked up the voltage. And when it goes, there's a hell of a flash, and the entire room shakes, as you can imagine. And the room is bigger than this. So, wide variety of interests. Something which has come on the horizon more recently, was announced a couple of months ago, is the Astute project, of which we're part. In fact, we're the 3rd biggest partner after Cardiff and Swansea. Astute is an Assembly Government funded programme, but through the European Funding Office, WFO, to support SMEs in the convergence area. We're the blue blob just on the right of the picture, so we're just outside of the convergence area. But a lot of the people we work with are inside it. And the idea is to help them to more sustainably and more economically manufacture composites or anything else. So it's a manufacturing program rather than simply a composites program. And if anybody here wants to talk again afterwards, you'd be very welcome to do so. So there are a whole range of things we're interested in, and a whole range for which carbon fibre is going to be important. So there's aircraft, wind power. Wind power is coming to North Wales in a big way. Automotive, not so much, but other transport applications. So I thought I'd just show you this, which is a map of the UK showing where all the carbon fibre factories are. There is actually one carbon fibre factory. It's up in Scotland, but it doesn't produce a suitable grade for aviation. So we have a big problem as a country. We have a prepreg supplier on our doorstep, Cytec in Wrexham on the industrial estate, and there are others around the country, but we have no supply of carbon fibre as a country. So I thought I'd just bring that up, and I'm sure if you want to chat afterwards, Andrew will talk to you about that one. So some conclusions then. According to my wacky definition of composites, most aircraft have had some form of composite in the structure. We can only see that increasing because of the pressures and CO2 emissions and economics. And the last thing is a message for aircraft manufacturers, which is to beware of tram, bicycle, car and bus makers, because they're next year's competition, either for the fibre or for the business. Okay. So I'm just going to finish off with that, which reminds me to shut up. Thank you very much.
Richard has kindly agreed to take some questions from the audience this evening. So we have a few minutes for questions, and after that then we will have some time where there's some refreshments and some talking time outside. So does anybody have a question they'd like to offer Richard?
How do composites compare to metal with regards to fatigue and fatigue lifetime?
Generally, it's not such a problem. One of the things I remember doing is teaching a lot about fatigue of metals in a degree course, but actually fatigue of composites isn't taught a great deal. And it's, to some extent, it's because it's not such a problem. In fact, for a while, there was a company called Sulcated Springs who used to make truck springs out of glass fibre and epoxy, and they were actually better than the metal ones. But I don't think the company exists anymore, but the springs were very good and had very long fatigue lives. So it doesn't tend to be such a problem. It's manageable.
Can you envisage a time when the wings of airplanes will be totally composite?
Yes. For the Hondajet, they already are. For big civil aircraft, it's much, much more difficult. But for, say, the 350, which Broughton is gearing up for now, the spars, which is the bit that go along the length of the wing, and the covers will be composite. I think the ribs, which go the other way, will still be metallic. But so within a few months, they're going to be starting to put together wings that are largely composite.
You mentioned the different types of fibres, carbon and glass and wood and so on. But is that the range of fibres that there are? Are there any new ones in future? I mean, what would be the future direction for fibres? Is it just the ones you mentioned, or are there others that could be developed?
There tends to be a fairly limited range of fibres, whereas the matrices, the resins, there's a whole variety of them, lots and lots. So glass dominates for most applications where you're not trying to move it. Carbon for structures you're trying to move, but there's also Kevlar. Basalt fibres have come onto the market now, but basalt fibres are not much stiffer than glass fibres. But there's kind of limitations. And one of the problems is that nobody's really doing much research and development in the area. Certainly in terms of carbon fibres, there's not much going on to produce newer, better carbon fibres. It's quite limited.
There is a boron looking into, isn't there?
Sorry,
Boron.
boron fibres were used in the 60s and so on. And for instance, in the tailplane of the F-14 it was used. But boron is not very good for you. And trying to get hold of boron fibres now is quite difficult because I had to try and source them for a project a couple of years ago, and the supply now is very limited. But at one point it was, a hot topic.
I would remember in my days in aircraft that bonding was a very important feature, especially if you had a lightning strike. How do you go with composites? Do you have to put a metal mesh in them or something?
There tends to be a bronze mesh in the surface of the wing to cope with that, because you tend to get lightning strike above the cockpit, and then it tends to work its way through the fuselage and out through the wing. And so you have to put this in, but when you actually put the composite together, very often the bonding, the earth bonding across there is a difficult subject. So it remains a challenge. It can be done, but it's not straightforward.
How do you recycle these structures?
Well, one question is, do you want to? Because if you look at cars, say, you have a lot of cars on the road, and then they have a fairly short life, and it's a big problem. But with aeroplanes, the entire fleet is probably about 35,000 or something, roughly. I can't remember exactly what, for so the big commercial jets. And they have lives of 40, 50 years, certainly more than 30. So although they're big structures, actually it's not such a big problem, although it will become more so over the coming years. At the moment, they tend to store them in the desert in America and then go around and scrap them. But clearly, with the composite aircraft, this problem's going to come and rear its head. And so I don't think it's a big problem in terms of volume compared to other sectors, but it will become a problem. And certainly, I've done some research on recycling, and that there is a company which will take your material and get rid of the resin and give you the fibre back. I can't remember their name. They used to get it under the name of milled carbon. Carbon fibre recycling. I knew they changed their name. Thanks, Paul. So I'll say some of the research that will be done here will be into the recycling, but I think you also have to get it into context.
How does the repair of composites stack up against traditional sort of metallic repairs?
Again, it's an interesting area, but there's a lot of work going on repairing places. It's not so straightforward, because how do you then verify that your repair is okay? And very often you end up riveting a patch on, something like that. But it's a challenging area, and again, it's one that we're moving into.
Are there any particular non-destructive techniques used in evaluating the composites?
Very similar ones to metals, actually. So ultrasound is used a lot, and X-raying them, two key techniques. So it's the same as you would use for a metal component.
Next extension to my earlier question. Take the A380 for instance. If the wings were fully composite and the aeroplane was fully landed and it's going through incredibly severe turbulence with vertical up and down drafts, honestly, is it as strong as the aluminium made wings that we have currently?
Yeah.
Because I have doubts about it.
Yeah, no, it would be okay. The Achilles heel for composites is hailstones and hailstone strike and damage. And the composites that are used are actually thicker than you would need just from a structural analysis point of view, and it's to resist the hailstone strike. So that's the limiting factor. You just have to make sure it's thick enough.
So when you say, what sort of thickness do you mean?
I
30
can't,
millimetres? Or?
I can't remember off the top of my head. I think it might be 11 millimetres to resist the ice.
Do you get any deformation with age of panels?
Something which can happen in polymers is you can get creep, where if there's a load on them for a long period of time, they can move. But because you've got the fibres there that don't tend to, then it doesn't tend to be a problem. Only if it's very, very hot.
Are the problems with health and safety whilst you're working with composites for processes like repairing, cutting them and the dust that they give off?
Yeah, you have to be careful with the dust, but you have to be careful with the dust in a lot of industries. Again, if you were to come around the facility at Harden, you'd find that the way we operate there is whenever you're drilling, there's actually extraction on the tooltip, and the dust gets taken away, so it never gets into the air. So actually, the operators don't have any kind of protective equipment. It's all taken at source, and provided you do that, you can walk around quite happily.
Richard, I'm interested in the thermal range because of composites, because the next stage up from aeroplanes is space travel.
Yeah.
And that's potentially a market to be opened up for investment in coming years, leisure and tourism as well. Can you see composites being involved in that?
Yeah.
Or are there sort of thermal constraints?
I used to work on this, so I can tell you the answer. Thermal constraints with the materials which say go into that sort of plane, probably you wouldn't want to run them above 100 degrees C. But some of the materials I was working on probably 20 years ago was with the aim of reusable space vehicles, and that can be done, but there are challenges because they're quite brittle materials and you have to protect them.
And I guess that would then lead on to engine manufacture and the ability to replace metallic elements of engine manufacture with composites, would it?
Potentially. I think the sort of composites you'd use for that application are probably a bit brittle to use for turbine blades. But you can see a day maybe when the fan cases and so on could be composite. In fact, NASA did some work on it a while ago.
Is water absorption a problem with composites?
It can be, yeah. So one of the key tests for composites before they actually get adopted is that you do some mechanical tests to make sure that they've got the right sort of properties. But then normally you would leave them in a hot, wet environment for maybe a month or two, and then go back and retest, because water can attack some of the matrices. So you go back and check that it hasn't for that particular material, and you redo all the mechanical tests.
So what typically is the percentage weight gain, for example, after these tests in high and humid conditions?
I can't remember off the top of my head. It's about 1% or so. It's not very high for these kind of materials. You have to remember 60% of it is the fibre anyway, and that doesn't really absorb water.
Do you use a lot of gluing techniques on this, or do you actually drill and rivet? And if you do drill and rivet, where it's a composite going onto a metal, or worse still, a metal onto a composite, how do you cope with the breakout of the drill and the composite material? Because I notice on fiberglass it's a big problem on boats sometimes.
Yeah. I have to say that generally in big aircraft, you drill and rivet like in a metal aircraft, and that's just crazy. But the reason that comes about is because obviously you'd like to glue it really, but the problem comes back to non-destructive testing. How do you prove that you've stuck it together? So that you can make the CAA happy, because they won't let you fly anything that you can't prove is stuck together. And at the moment there's no technique, so you end up having to drill holes and rivet things. Because riveted joints sound terrible, but one thing about them is that they do fail in a very controlled and stable way, whereas glued joints, when they go, they go. So you have to be really sure you've got it right, and at the moment we can't be. And again, drilling, a lot of it's down to technique and using the right drills.
Have you got a view as to how composite aircraft fare through turbulence? So with a metallic aircraft, because of the flexion of the structure, it'll absorb a lot of the motion, if you like, as it goes through the turbulence. With carbon fibre, I believe it's a stiffer structure, and it's not going to be absorbing that sort of movement as well. So I'm led to believe there may be a harder ride, should we say, through turbulence. Have you got a view on that?
No, it's not an area that I'm very familiar with, so I can't really offer anything on that one. Sorry. I suspect there's a few people in the room who might be able to. I'm not going to look in any particular direction.
I invite 2 more questions and then we can...
Is there an issue with corrosion where you have a metallic structure against the composite structure?
That's something you have to be very careful about, because obviously they've got different potentials. So when they're assembled, materials are put in to keep them apart. So you have a mastic that goes in there that keeps them apart. And the same when you put the rivet in, there's some mastic in the hole. So if you keep them apart, it's fine.
One more question, Peter?
Yeah, Richard, when I was a lad, carbon was a real low-tech material. It was battery anodes and the charcoal used in art class, and otherwise we knew it was inorganic materials, but that was all fluffy stuff, not real engineering. But carbon fibre's come up in the last few decades. Seems to have arisen in interest in parallel with Buckminster fullerene, nanotubes. Is there any connection? Can we make superior carbon fibres by growing long nanotubes, or are these entirely separate things that have just occurred coincidentally together?
There's a bit of coincidence, but when you look at the structure, actually the structure is very similar in that the carbon fibres basically have sheets of graphite in them, and all nanotubes are those sheets rolled round. So there's a lot of commonality, and there's a lot of work on carbon nanotubes. In fact, I don't know if Foward's here. There he is. But one of the people that we've just taken on, it's his research area. So watch this space.
Good.
Okay, well, it's time to draw this part of the evening to a close. And I guess I'd like to express, first of all, my thanks to Richard for an entertaining lecture. I jokingly said to him, if he keeps me interested after 20 minutes, he's doing really well. I was fascinated for the whole hour and 5 minutes, so thank you ever so much for that. And it's been a pleasure listening to some of the background you've had and the work you've done thus far. So thank you.